Good morning, Madam Tan and my fellow friends. Today, me and my friend Nur Fatiha are going to present about the assignment tools calculation. In this presentation, I am going to present the calculation for question 1 and 3, while Fatiha will present question 2 and question 4.
Hydraulics is a branch of science and engineering that deals with the mechanical properties of liquids, especially the use of liquid fluid power to perform work. It involves the study and application of fluid motion and pressure to operate various systems and machines, such as pumps, hydraulic presses, and braking systems. Hydraulics plays a vital role in fields like civil engineering due to its efficiency in transmitting power and control through incompressible fluids like oil or water.
In question 1, we need to determine the bed slope required to maintain the discharge under uniform flow condition. Firstly, we need to determine the area of circular sewer pipe, which is area A is equals to pi r square over 2. Next is wetted perimeter, which is 1.8850 meter. Then, determine the R, where A over P, so 0.5655 over 1.8850 is equals to 0.3. Lastly, we need to use formula where Q equals to AR 2 over 3 times square root S over N. So, slope is equals to 0.0085.
Next, question 2, which is determining the best hydraulic section for a trapezoidal channel using Manning's equation and the trial and error method. Let's begin by looking at the data provided. We are given Manning's roughness coefficient and that equals to 0.012, design discharge Q equals to 10 meter cube per second, channel bed slope that equals to 0.0005, bottom width with 5 meter, and the side slope given as 3 vertical to 2 horizontal. This gives us a side slope ratio Z equals to 2 over 3. Our goal is to find the depth Y that results in a flow of 10 cubic meters per second using the Manning equation for open channel flow. So the formula given, Q equals to 1 over N times area times R power 2 over 3 times slope power 1 over 2. To use this formula, we need to find the flow area, which is area equals to, in bracket, B plus Z times Y, the wetted perimeter P that equals to B plus 2Y square root 1 plus Z square, and then the hydraulic radius, which is equals to area over wetted perimeter. After that, include the hydraulic radius R equation into the Manning equation formula. And next, plug all the data given into the formula and calculate each part. Calculate this part carefully because it has power for each section. After the calculation, separate the part where it has Y unknown value. Now, move the whole number to the right and calculate them to find X. After we calculate, we will get 5.3666 for X value. Since Y is unknown, we use the trial and error method by testing different values of Y, then computing the corresponding discharge Q. We have tried several numbers to find the Y that equals to flow rate of 5.3666. So we have tried 1.25 meter, 1.22 meter, 1.15 meter, and so on. So the last value that we tried is 1.078 with exactly 5.3660 flow rate. So after tried several value of Y, finally we get the same flow of 5.3660 meter cube per second with 1.078 meter value of y. And lastly, we have to go through the full Manning's equation again to verify how the flow was calculated, and finally we will get the final answer, which is 10 equals to 10. Now we have to find the water depth y for best hydraulic trapezoidal cross-section based on the given slide slope. So using formula b plus 2zy equals to 2y square root 1 plus z square, just plug in the side slope data, which is 0.67 into z, and then solve the equation and calculate till we get y equals to 4.68 meter.
Next is question 3. In this question, we need to calculate the specific energy, critical depth, and alternative flow depths, indicate location of flow, minimum value of specific energy, and critical velocity. For specific energy, E is equals to y plus v square over 2g. So, E is equals to 5.7998 meter. Next is determine the critical depth, but before that, find Q first. Q is equals to y times v, so 1.2 times 9.5 equals to 11.4 meter square per second. Then, for YC, 11.4 square over 9.81 power 1 over 3 equals to 2.3662 meter. For the alternative flow depth calculations, Y1 is equals to 5.587. Next is the minimum value of the specific energy head, where 3 over 2 times 2.3662 is equals to 3.5493 meter. Last but not least is the calculation for critical velocity, where square root 9.81 times 11.4 is equals to 10.5752. Since y is smaller than yc, the flow is indicated as supercritical. The diagram shown the specific energy for all the following parameters.
So for the last question is Swissgate. The data given is width with 3.0 meter, Q equals to 5.6 meter cube per second, and slope at 0.0005, and the coefficient is 0.025. So the formula that we use here is Q equals to area times 1 over n times r power 2 over 3 times slope power 1 over 2. So here we can get the area with y times 3, and the wetted perimeter is 2y plus 3. So the hydraulic radius will be 3y divided by 2y plus 3. And then we will use the same exact formula and solving pattern as question 2, which is after solving the calculation, we have to separate the part where it has y1 unknown value and moving the whole number to the right and calculate them to find x. And after the calculation, we will get 2.0870 for x value. So since y1 is unknown, we use the trial and error method, then computing the corresponding discharge, Q. And after try several value of y, we finally get 2.241 meter of y and 2.0868 meter cube per second of flow. Next, calculate the yc value, which is cube root q square divided by 9.81, and we will get 0.7082 meter of yc value. As you can see, the y value, which is 2.241, is bigger than yc, so it is not y1. So we try to find y1 using the formula negative y2 over 2 plus square root y2 square over 4 plus 2b square times y2 divided by g. So we can get the velocity by using the q equals to area times velocity formula. Then plot all the velocity and y2 value using the y value that we get just now, and final answer will be 0.1335 meter. So it shows the value is smaller than yc value, so that's how we determined the y1 value. Next is equitable water resource allocation. In hydraulic engineering, ensuring equitable water distribution is not only a technical challenge but also an ethical imperative. When performing calculations for uniform and non-uniform channel flow, it is essential to consider how water will be allocated across various users and regions. Accurate modeling of flow rates, channel capacities, and discharge patterns support fair distribution among agricultural, industrial, municipal, and ecological stakeholders. For example, flow routing in non-uniform conditions must account for downstream users who rely on consistent water supply. Over or under-designing a channel can unintentionally favor certain groups, leading to resource conflicts or deprivation. Integrating equitable allocation into the design process promotes social justice by ensuring all communities, especially those historically undeserved, have access to the water resources they need to thrive. The last one is community involvement. Hydraulic design should not occur in isolation from the communities it affects. Engaging local populations during the planning and design phases enhance both the quality and acceptance of the final solution. For instance, in determining flow velocities, channel paths, or flood mitigation measures, the input of residents who understand the local landscape and water use patterns is invaluable. Community involvement ensures that technical assumptions reflect real-world needs and priorities. Additionally, by presenting hydraulic modeling scenarios, such as those showing impacts of gradually varied flow or backwater effects, engineers can build trust and foster collaborative decision-making. Ultimately, community participation leads to designs that are not only technically effective but also socially responsible and culturally appropriate.
The third point for ethical consideration is public safety, which is vital in hydraulic engineering, especially when designing systems near populated areas. Accurate calculations of channel flow help predict depths, velocities, and flood risks. Without proper modeling, communities face dangers like flooding, erosion, and infrastructure failure. Engineers must consider worst-case scenarios and include safety margins, freeboard, and floodplain buffers. Design features like safe flow paths, spillways, and warning systems are based on this analysis, ensuring the protection of lives, property, and livelihoods. In conclusion, hydraulics is a crucial field in engineering that enables the efficient transmission of power and control through the use of liquid fluids. Its wide applications in machinery, transportation, and infrastructure highlight its importance in modern technology and industrial development. So, that's all from us today. Thank you.